Hello, everyone. So I got some questions about the design of the CRC circuit and how to use how to use it to calculate the CRC. So I'm referring to the slides here. Let me share my slides with you. So I'm referring to the circuit here that you can see. So how to build the circuit and how to do these calculations, right? So I'm going to go through this in this video, and I'm going to go over an example that's similar to this one, and hopefully that will clarify how to build the circuit. Okay, so first of all, let me explain what is we need registers, we need shift registers, right? So what are the shift registers? So for those who are not familiar with the shift register, is a logic circuit, right? There are many types of them, but we'll just consider an example where we have a single input, a single output, and usually there is a clock or an enable signal that tells the register to store the information inside, right? So the circuit saves a bit, 1 bit of data. So if it has the input, if the content right now is 0, right? So the output will be exactly the same as the content, so will be 0 as well. So if I'm reading the output here, I will find that the output is the same as the content of the register, which is 0, right? If I want to change the content, I'll put the input bit, let's say it's 1, right? Once I put it in the input, doesn't go inside right away. I have to enable or hit a signal, right? Which usually comes from a clock. So in some circuits, the clock will, or the circuit, the shift register will recognize a transition from 0 to 1 when there is a clock. When the clock usually is 0, 1, 0, 1, 0, 1, like this. So every transition will tell the register to take the input and put it inside, right? So the input will change, and now it is 1, and the output will be exactly like the input. So if I have, if I want to change the content again, so the next rise of the clock, the whatever input, if this is 0, another 0, so at the second clock, the content will change, become 0, and the output will become 0 as well, right? Okay, so that's the basic idea of the shift register. Now, as I mentioned in class, how to design this circuit? Well, we take the polynomial, like the one that's shown to the left here, 0, 1, 0, 1, 0, 1. I put the bits far apart in purpose. So in a polynomial of 6 bits like this one, the register, the CRC is 1 bit less, right? So we need the output, the outcome will be 5 bits. So we need 5 registers. So we put a register between each 2 bits, and we call them C0, C1, C2, C3, C4, right? And in front of each one, we'll put an XOR operation, except the last one. Then we connect everything. The output of the last register connects to all the XORs, right? That's very important. Okay. So the design again, put a register between every 2 bits to represent the outcome. then put an XOR in front of each one in the polynomial except the last one. Then connect the output of the last register to all the XORs. Okay, so now I'm gonna go and go over the steps using a simple circuit. This has 5 registers, which is, if you do it manually, is gonna take a long time. So I chose an example where we have less registers. You see here that I did the exercise before, so I'm just gonna delete my exercise and start from scratch. Okay. So my polynomial here, if I do the long division, so this is my data bits, and this is my polynomial. So the data bits here, let me highlight them a little bit. So these are my data bits. And so this is my message, right? And the polynomial is this part. And as we saw in the lecture, before I do the division, I have to shift the message by a number of bits so that I can leave space for the remainder to be plugged in. So how many bits I need to shift? Well, it's the polynomial size minus 1. So the polynomial size here is 5. So I need to shift the bits by 4 positions. So when I do the division, I'll write down the polynomial. And then extra 4 bits. And then divide by the 1, 0, 1, 0, 1. So that's the long division, which results in this number here, right? Okay, but I don't want to do long division today. I want to use the circuit. So we're going to trace the circuit and we use it to explain how things work. Okay. So I'm going to share with you now only this part, right? And we're going to go over the steps. So I arranged my data vertically here. This is the time steps. So imagine there's a clock in every time step. The clock is used to change the content of the register, right? And here's my circuit. So I used the same method that I used before. So I took put a register between each 2 bits, and I put XOR in place of each one, and I connected the last register with all the XORs, right? Now, initially, we'll reset the registers, so all of them will start with a value of 0, and then we'll start the operation. So the operation starts by looking at the input here. So the input, the data bits will start from the first bit to the last bit and going in from right to left, right? So the input here is 1, which is, if you look at the data here, this is the input, right? So the input will come in, and there is an XOR operation here with the output of C3. So if you look at all the XOR operations, you're XORing, first of all, you're XORing the data input with the output of C3. What is the outcome of the XOR is 1. So we put it here. 1 will be XORed with 0 here, which is C3. So the input, so the result will be 1. C0 will go straight to C1, so 0 here, and C1 will be C1, the content here, will be XORed with C3 because we have the XOR operation here, so that's a 0. And then the output of C2 will be going to C3. Okay? I'm not sure how I made that mistake, but anyway, glad that I fixed it. Now, in the next clock cycle, we have the input. 0, and again we follow the same steps. So the input to C0 the next time will be the 0 here XORed with C3. So 0 XORed with C3 is 0. Whatever in C0 at the time, which is 1, will go to C1. So that's 1. And the C1 content will be XORed with the C3 content. So 0 and 0 will be 0. And the 0 here with C2 will go to C3. Now, step 2 will take the 0 here XORed with the C3, and we'll just put it in the next time step. So 0 and 0 is 0. And the content of C0 will go straight to C1, so that's 0. And the 1 here will be XORed with C3, so we'll get 1. And the 0 here of C2 will go straight to C3. Okay. Now we'll move our attention to step number 3. So the input is 1, XORed with 0, we get 1. And this content will go straight here because we don't have an XOR operation. Here we have an XOR operation between the 0 and the 0 here will get 0. And we don't have an XOR operation here, so the 1 goes straight. Next time step, which is 4, we'll take 0 and 1 here is 1, and 1 from C0 will come down, and 0 with 1 is 1, and 0, there is no XOR, so we take it down straight. All right. So just double checking the 0 XOR with 1, we get 1, the 1 comes down here straight, the 0 with 1 is 1, and the 0 comes down here. Okay. Now just make sure that you don't miss any steps here. Now here we have 1 XORed with 0 of the C3. So 1 with 0 is 1. The 1 from C1 goes straight. The 1 from C1 XORed with C3, so 1 and 0 is 1. And the 1 from C2 goes straight. Now the input of step 6 0 and 1 is 1. The one here comes straight. 1 and 1 is 0. The one here comes straight. And if I follow this pattern, so now 1 and 1 is 0. 1 comes straight. 1 and 1 is another 0, and 0 comes straight. Now 0 here with 0 here XORed, so we end up with 0. The 0 from 0 comes 0, and 1 with 0 is 1, and the 0 comes straight. So I'm gonna go a little bit faster now. 1 and 0, so this 1 here and 0 is 1, and the 0 and the straight, and the 0 from here is XORed, so it's 0 here and 1 without an XOR. Now I'm looking at this step, so it's a 0 XOR with the 1 here, so it's 1, and this 1 goes straight, and this 0 is XORed as well, so it's 1, and the 0 goes straight. And now the 0 from step number 11 0 and 0 is 0. The 1 comes straight. The 1 and 0 is 1, and the 1 comes straight. And then step number 12. So 0 and 1, we end up with 1, and this 0 here, and this 1 with 1 is 0, and 1 comes here. The final step is 0 and 1 is 1, and 1 comes down, and 0 and 1 is 1, and the 0 comes down. So we end up with the final result at step 14. And the final result you see here, it's the same as our result in the division, but 0, 1, 1, 1, which is same as here. So I hope that explains how the circuit works. You have to be careful not to miss a step. So I hope that's helpful in explaining how the circuit works. You need to understand how to design the circuit. Tracing the circuit is a long process. So I just meant to explain how the circuit works. But of course, this is done by hardware. So in practicality, nobody's doing that by hand. But just it meant to explain how the process works. Right, so hopefully that's helpful, and that's it for now.